Okay, guys. So momentum as a letter, don't ask me why, but it's given P. It is the product of mass and velocity. So, little warm-up, it's worth looking at. We got three separate items here. We got a feather, a marble, and a softball. Okay? We have three choices of speed. Given a choice from column A and a choice from column B, which combination would hurt the most if we threw it at you? Jeff? Pay attention. So, some of you guys like a marble over a softball. We probably want, if it's going to hurt the most, so on our pain scale, the most massive probably is going to hurt the most with the fastest speed, right? Okay. The reason why some of you are thinking maybe the marble's going to hurt more is because you understand this concept called pressure, which is surface area. It's like it has to do with the surface area as well as the mass. Okay? That's why, like a bullet, if it was the size of a beach ball, it would knock you a block away, but it probably wouldn't kill you, maybe. The reason the bullet kills you, okay, maybe it will. But the reason the bullet kills you is it actually goes through you and destroys organs, right? Based on its size. It's got a lot more pressure because all that weight is concentrated in a very, very small area. Just in the top of my head, because it's snowing, if you ever watch rally racing on TV, World Rally, and you get these 400 horsepower Subaru WRXs, you ever see what kind of tires they use in Finland when they go in the snow and the ice? I'll give you a choice. Either the tire looks like that, or the tire looks like that. Which one do you think is going to give you better traction in the snow, A or B? B does. And that's opposite to what a lot of people think. You think the bigger the tire, the more tread you have. But when we're talking pressure, you want a lot more pressure. You want to be like an ice skate on the ice. Okay, you want small, small, small area because it sinks in. You get more pounds per square inch, to use an American unit. Okay, and better bite. It sticks better. It goes right through the snow, sticks right through it, sticks better on ice. Okay, smaller contact area. So, okay. So for the marble people, you're not necessarily wrong. Okay, depending on where the marble hits, yeah, maybe it would be more painful. But I think most of us would agree the more massive object and the faster the speed. Now let's look at our formula. Momentum is a quantity of this times this. If these are both big, and if P, momentum is directly proportional to M, what happens to the momentum if the mass doubles? It doubles. What happens to momentum if the velocity doubles? It doubles. So if this is times 2 and that's times 2, what happens to momentum? Times 4 times as much momentum. Okay? Here's Newton's, well, let me ask you, what is Newton's second law? F is ma. When Newton came up with this, he actually didn't have A here. Because what is the definition of acceleration? Change in velocity over a change in time. That's actually what he had in here when he came up with his formula. M delta V over delta T. He called this mv a quantity of motion. We call it momentum. Okay? So that's where this kind of comes from. And we know, like in football, the bigger the guy is and the faster he can run, probably the better player he's going to make on the field. Anybody watch football on the weekend? Don't watch CFL stuff? I don't either. Yeah. Okay, but the bigger, the more massive the guy is, the more inertia he has, the harder he is to move. Okay? And if he's running and he's got all that inertia and he hits you, look out. More massive, faster speed. Okay? So, that's what I just wrote. First of all, let's start here. This is, come on, yellow. That's momentum. Now it does say change in V, but if I say what's the momentum of a 50-pound, well, let's go kilograms, 50, can you see that? No. What's the momentum of a 50-kilogram guy running at 2.5 meters a second? Don't say, well, he didn't change his speed, therefore the momentum's 0. Because we can argue he went from 0 to 2.5 meters a second, okay? So the momentum, just multiply them together. What's the units for momentum? Kilograms, meters per second. If you're not getting those units, make sure you convert them, okay? So like I said, because acceleration is velocity over time, we can go F is ma, or because m times v is momentum, there's like another formula. Okay? Now, what happens if the momentum changes? Well, we got a word for that too. A change in momentum, we got a word, it's called impulse. If this guy that was 50 kilograms was running at 2.5 meters a second, that's 125 kilogram meters a second. That's the momentum. How much momentum would it take to stop this guy? What is the impulse that needs to be on this fellow to stop him? If I want the final momentum to be equal to 0, how much momentum did he have before? Initial, or like we use O for initial, right? Not I. I'm used to seeing I here. It just makes sense, but I know our book says VO for initial, right? And VF for final, so let's be consistent. So what's the change in momentum? If I want him to have 0, 0 minus 125, so the impulse or change in momentum is just negative 125, right? So there's a formula. We got 4 variables. We might say, what's the force necessary given the speed, given the mass, given the time? We might say, what is the velocity change given the mass, given the force, given the time, okay? So units I already talked about. Let's just look at a couple of quick ones here. I already did this. What's the momentum of 112 kilogram at 3.6? Just multiply them. They won't get any easier than that. What impulse must a tackler impart, that's a weird word, to the football player to bring him to a stop? I just did this, didn't I? Impulse, by definition, is the change in momentum, which is final minus initial. If he's at a stop, how much momentum does he have? 0. Because if V is 0, then that must be 0, right? Just like Newton's second law. If there's no net force, then the acceleration must be 0. Same kind of concept, because the mass can never be 0. Okay, so final is 0 minus, how much did he have before? I don't know, I didn't work it out, but it's easy to do. That will be negative, right? If the tackle was completed in 0.8 seconds, what average force, well, let's just use that, did the tackler exert on the other player? Well, let's look at our formula. F delta T is M delta V. What is M delta V? That's our impulse. That's our change in momentum. Okay? So F as a formula, divide by T, that's momentum over the time. I have the momentum, I have the time, plug them in and get the force. In this case, it's going to be negative, right? Okay, we want to know what the force is. There's our formula. Okay, if I want the force, divide by time. So F is, because mv is momentum, substitute that in. I already know the momentum. I've done that up here. Okay, and now I got the time. So the force required to stop this guy, bring him to a stop, is the change in the momentum divided by how long it took. That's actually the formula on my physics shirt that I got a couple years ago, if you guys noticed. All right? So force is, how quickly can you do this? That's the amount of force required. Okay, the stronger the person, the quicker we can bring this moving mass to a stop. And if it takes you a long time, then you have a lot less force to exert. Okay, so I didn't work out the numbers, but like I say, you know how to put that in your calculator as well as I. Why is it negative? Well, to change that momentum, you must put the force in the opposite direction, right? So we know by convention, if one way is positive, then the other way must be negative. So part one, I want you to do the simple little questions on the other page here. Those guys. Page 122, 1 to 3. 126, 1, 2, 5, 7. And 10 and 11, 128.